Hi everyone, welcome to my talk, Next Generation Mobile Rootkits. My name is Thomas Robb. I do embedded security, like hacking payment terminals. I do a bit of distributed computing and mostly breaking stuff, like GPU clusters for breaking encryptions and similar things. And for sure, as almost everyone, some web stuff. If you want to socialize, you can find me on Twitter or afterwards on a beer. So let's start with the prologue. Mobile rootkits, is that a thing? I think 2 years ago there was quite some buzz around Carrier IQ, which was a small rootkit installed on, I think, almost every phone, BlackBerry, Android devices, and so on. And yeah, it seems that mobile rootkits are currently used for usage statistics, if one believes what they say, surveillance for sure, for law enforcement, and criminal data gathering and malware. If you have your credit card on your phone with NFC, I think there are a lot of people interested in stealing the paper secret from your secure element. From my point of view, there are two interesting targets for rootkits on mobile devices. One is the baseband, that's the communication processor, which does stuff like 3G and LTE, and the CPU. The baseband, interestingly, seems to have direct memory access on almost all mobile phones. So if you manage to get a rootkit into the baseband, you can access the entire memory, but unfortunately not the peripherals around the CPU, like secure elements and so on. In this talk, I'm going to target a new part in ARM CPUs called the trust zone. Short question, how familiar are you with ARM? Like, who has never heard of ARM and coprocessors and stuff? Great. Chapter 1, Trust Zone. What is Trust Zone? Trust Zone is a secure processor integrated into Cortex-A series ARM CPUs. And the cool thing about Trust Zone is that it's not just a dedicated crypto processor in the CPU. It's more like a second core in the CPU that allows access to all the peripherals around the CPU. So you can use it for secure keyboard entry, for secure display, and so on. It tries to protect against malware, trojans, and rootkits, ironically, and so-called TEEs, trusted execution environments, run on it. Trust Zone splits the CPU into two so-called worlds, the secure world and the normal world. And you can communicate between both worlds using shared memory, so you can have small parts in memory where the normal world can write to, and then the secure world does some crypto magic or something similar on it, and then you just the secure world puts it back into the shared memory, and the normal world can send it by email or whatever. Another very cool thing is that the state of the CPU, so whether it's in secure world or normal world, is indicated to all peripherals. This allows you to have either on-chip peripherals and off-chip peripherals, which are only available to the secure world. So, for instance, you can have a small storage for secret keys, which only the secure world can access. About these trusted execution environment, it's quite difficult to get data on all the commercial ones, because they're like, yeah, we have this trust thingy and we put it in your CPU and everything is cool. But yeah, there's trusted logic, trusted foundations. That's a quite famous one. There's Gemalto and GND. With their MobiCore TE, and then there's a global platform API. So if you know smart cards, you will know most of the names on the slide. And the idea is that you write apps for these trust execution environments and then pay whoever. I honestly don't know. I wasn't able to find any resources on how I could get my own trustlet into this trusted execution environments, but you pay someone to integrate them. So for instance, if you have an email client, you could build your SMIME stuff as an app for this trusted execution environments, and then your Android application or your Windows Phone application will just call the trusted execution environment for all the crypto magic. They're used as using a driver on Android and Windows, and if you're interested in reading about such stuff, the MobiCore driver is actually open source and can be found on Google Code. A concrete example, Netflix is an American streaming service. I think in Europe it's almost not used or even not available. And Netflix requires device certification. So if you have a mobile phone or you build a mobile phone and want to show Netflix on it, you need to ask Netflix for certification. For the low quality standard definition videos, it just has to work. So you basically go to them, show them, here, my device is fast enough, your app runs fluidly, and so on. Everything is fine. But for HD streams, the labels require end-to-end DRM. So that the video stream can't be video grabbed by some Android application or by Windows Phone or using USB debug, whatever. And the idea is that the video decoding runs entirely in Trust Zone. So you start the Netflix app, select the stream you want to watch, and then all Android does is push the data into Trust Zone, and Trust Zone then decodes it and writes it directly to the screen without using the Android graphics subsystem. And because of that, you can't record the video streams on the Android side. So who does Trust Zone protect against? Device owners. So basically you're getting locked out of parts of your device so that they can do copy protection measures and DRM. And for sure malware, so that no fancy Google Play, I don't know, game or something can steal all your payment information. So let's get a bit technical. How does it work? In most implementation, it feels like a second register set to the CPU core, to the first CPU core. If you have a multi-core system, only the first one will be used for Trust Zone because according to them, it's just very complicated to implement it on a multi-core system. To switch between both worlds, there are two possibilities. One is the SMC instruction, secure monitor call, and the second one is a hardware exception, like interrupts, fast interrupts, external data aberts, and so on. And for indicating the CPU state to all peripherals, there was an extension to the AXI bus, that's the internal bus on ARM chips, called the NS bits, which indicate whether the operation that the CPU wants to do on peripherals is a secure write or secure read or a normal read or a normal write. Unfortunately, the AXI to APB bridges don't support it. APB is the slower bus on the chips, so you have to be aware of that if you happen to design such stuff. Switching between both worlds is not straightforward. You can't just flip over to the secure world because you have to manage the state of both worlds. Like if you're in a normal world and want to go into the secure world, you always switch using the so-called monitor mode. The monitor mode is it's an additional mode besides the privileged modes in normal and secure worlds. It's basically a very small code fragment that will save the state of the normal world, like store, register stuff, maybe disable some external peripherals, and then give execution over to the secure world. Memory in Trust Zone, I think I mentioned it earlier. Here you have a sample configuration or how you can map the memory using a Trust Zone supported MMU. You have the normal world memory, which is accessible from the normal world and the secure world. You have the shared segment, which can either be writable or readable from the normal world. And then you have the secure only memory, which is only accessible from the secure world. So In short, the normal world only sees its own memory, so it can't even detect whether there's a block of secure memory. It doesn't know, it can't detect it. It will just give a data abort on the bus, and that could come from anything. And the secure world can access everything, so I guess you see why this is quite useful. To give you an idea how a normal trust zone setup with secure boot runs on a modern mobile phone, you have the first stage bootloader, which is contained in the read-only memory. It lays some hardware abstraction stuff, and then there's integrity verification of the second stage bootloader, which is normally contained in Flash and can be updated using firmware updates and so on. And yeah. In the second stage bootloader, the initialization of trust zone takes place. The trust zone kernel is loaded into memory. All the secure registers and so on are set up. And then it loads and configures either the operating system immediately or a third application operating system loader. As you can imagine, this part has to be trusted. If you're able to modify either of those two bootloaders before the trust zone is locked, you will break the security and you can read secrets out of the CPU. Like there is keys fused into the CPU which you might be able to read out. By the way, some vendors provide you with the possibility to unlock your phone. You don't really unlock it. You unlock this operating system loader, at least in most cases, and all the entire boot chain with the trust zone setup and so on will still take place. So you can't even make sure whether if you run your custom baked Android ROM, whether there's not something running in trust zone which is, I don't know, stealing your data, maybe a rootkit. Hardware support. All modern smartphone CPUs have built-in support for trust zone. Qualcomm Snapdragon and TI OMAP. I have no idea about Apple's processors because they have no open specification. Does anyone happen to know whether they use trust zone or support trust zone? If yes, feel free to drop me an email. I will give beer for answers. Any questions so far? So, after taking a look at the trust zone technology, I think it's obvious why it might be interesting to place a rootkit into trust zone. Yeah, why? First, it's interesting. It's something new. It hasn't been done. No, at least with my Google skills, I wasn't able to find anyone who actually implemented something using trust zone, something evil using trust zone. People haven't talked enough about the problems that come with trust zone, because normally if you have a secure element and are locked out of it, that's okay. I mean, it's the same with your banking card. You don't really need access to it. But if you have this trust zone thing in your mobile phone, it means that the vendor has always access to the entire memory of your phone and can either spy on you or do usage statistics or whatever. And the trusted computing is not only about the user trusting the hardware, but also about the vendor distrusting the user, especially in this case, as it's almost impossible to disable trust zone on all major phones. So after having the idea, the first problem was where the fuck do I test my code? At first I thought, yeah, I will just go and get a Beagle board. They run on modern TI OMAP CPUs. And after some Googling, it turned out that there are two versions of all OMAP chips. One is the high security version, and one is the general purpose version. Even though both have the same silicon, as far as I know, the general purpose versions switch to the normal world in ROM already. So the ROM locks you entirely out of trust zone and disables all the stuff connected to it. And in production devices, the hardware is locked down with very strong keys, which are fused into the CPU, which you need to modify some of the stuff, like for the boot chain and so on. But QEMU supports ARM, and luckily the guys of Open Virtualization have written a paper, a flexible software development and emulation framework for ARM TrustZone, and that's an open source emulation for TrustZone running in QEMU. It's a bit experimental, and I had to hack on it quite a lot to get my mobile world, let's say, a mobile phone simulated in it, because it's more for virtualization. And there's also an open source trusted execution environment from the Open Virtualization guys, which is pretty cool if you're interested in such stuff, and it gives a good overview of what you can do and helps you if you want to get started with development. The first thing you have to think about when developing a rootkit in this separate area of the CPU is, how do I actually call my rootkit? I can't rely on the operating system or on some driver and on Android to do me the favor of switching into the secure world, like, I don't know, every 10 seconds, so I can spy on him and get back to him and so on. So so yeah, we need a way to switch to the monitor mode and to the secure world in regular or irregular intervals without the help of the operating system. So the entire thing that I will show is operating system independent. So you can spy on Windows, on Android, on BlackBerry OS, whatever you like, because it runs in a separate part. Also, the latency induced by the regular calls into the rootkit must be kept as low as possible, because if you induce too much latency, not only will the performance suffer, but it will also be assigned to anyone doing some basic analysis that something is going on there. And interestingly, even though it's for trusted computing, ARM actually gives you help on how to use TrustZone invisibly to the normal world, as they call it. So I don't know what that's useful for, except for spying, but yeah. And they also suggest that if you use interrupts to get into your rootkit, that you obfuscate the timing by like inducing latency into all interrupt calls instead just every 10 or so that the entire system gets slower, but you can't really pinpoint it to, there must something be there, because it has a variable length for the interrupts, so something evil is happening there. They also suggest that you cut the access to the performance counters. There's a small, very high-speed counters on the CPU, which you can use to measure the time several things take. For instance, if you build real-time systems, that's quite interesting. And cache maintenance, but yeah, we'll come to it later. So how do we get from the operating system into the rootkit without help from the operating system? We could use standard interrupts. They are used a lot by the operating system because, for instance, the system calls might be implemented using the standard interrupt facility. Also, the external interrupt controller will use the IRQ, and they can be masked by the normal world. So the normal world can disable the execution of standard interrupts, which might be a problem because it could be a denial of service for your rootkit because it's just not called anymore. On the other hand, no operating system will ever be useful without interrupts. Then there's the external prefetch abort or data abort. In my opinion, too unreliable as a single solution, because you just can't predict whether it will happen once a day, once a month, or ever. And then there's the fast interrupt facility. The cool thing is that TrustZone allows you to make the fast interrupt a non-maskable interrupt. So the normal world can't disable the fast interrupt execution. which comes in quite handy because you could configure a timer in the CPU, which always generates a fast interrupt, and you have a perfectly time-scheduled rootkit running on the device. Or you could overwrite the entire interrupt vector, which, in my opinion, Cloaker does this, a very cool experimental rootkit. But the problem is that if you overwrite the interrupt vector, you actually change parts of the operating system, and yeah, and that might be dirty. So to give you an idea how an IRQ interception, IRQ-based scheduling could look like, when the interrupt is triggered, the CPU immediately switches into the monitor mode. The monitor mode saves the state of the interrupt registers and so on, executes a small slice of the rootkit, restores the state, and calls the real interrupt handler of the normal world. So we'll get back to that later. Any questions so far about the scheduling stuff? The boot process is, when you start implementing it, the first thing you actually do. You have to learn how to set up the CPU world, set up the monitor mode, and then lock down trust zone, which is a very important part because you have to work with all the peripherals on the CPU and all the facilities that come with trust zone that allow you to do very fine granulated manipulation of the behavior on several things. For instance, you can prevent the normal world from reading out a lot of registers from the coprocessor. So let's start with the setup of the CPU world. The first thing you have to do is the memory setup, because you need a scratch space where your rootkit can collect data and so on. And for that we have to create a page table. The problem is that as soon as we work with the physical memory, we are changing the environment of the operating system, because the operating system will also try to lay out their own page table stuff, and may use as physical addresses, or tries to use physical addresses, which it thought were free. In ARM you can actually map external peripherals into the physical memory address range. And so you have to be very careful when doing this first step, so that the operating system can still boot. Because Android and co actually expect the standard Android distributions actually already expect to have address space reserved for trust zone. That's not really a problem, but if you're not, if you're unlucky, I would suggest using a physical address space right behind the hardware mapping, because that will be at least suspicious to a developer. This secure world initialization run a standard initialization routine, like load up some memory, create some structures in RAM and so on, and then configure a system call facility, because the rootkit I wrote has this provide a base system call facility to do stuff like read address ranges from the normal world, read data from the eMMC, which is quite some overhead. If you start implementing your own modules for the rootkit, you have to you have to do it all by yourself, and it's quite a lot of code. And because of that, I wrote this small system call facility, a small operating system, which helps you by providing stuff like FAT support on a MMC and so on. And yeah, currently work in progress is that actually the modules of the rootkit run in a separate environment, in a user privileged mode, but maybe in the future. Also, I decided to use timer-based slice scheduler. So basically, by default, the execution of the rootkit is always constant time. It always gets like, let's say, 2 milliseconds of time, and after that it gets back into the monitor mode to have this constant latency that people won't suspect anything. And it is able to store files in secure storage if it's available on some devices. On a system on a chip, you have actually a small micro MMC card integrated into the chip, and you can partition it and lock down these partitions. They are not like hard drive partitions. They're more like you can lock them down, and you can prevent the operating system from accessing them. And they're also TrustZone supported eMMCs, so you may even have half a gigabyte of space just for your rootkit, where you can collect all the things the user does and so on. After setting up the secure world, which is quite boring, you have to set up the monitor. And for the monitor, as mentioned for 100 times, it's very important to do latency reduction. Because of that, I decided to use tightly coupled memory, so very fast memory. Actually, I can even use the L1 and L2 caches, so all this stuff, all this save state, restore state is very, very fast, I think. The next thing we do in the setup is set up the interrupt interception mechanism, so configure the coprocessors around you to put the CPU into the secure world as soon as an interrupt happens. And I forgot to finish a sentence there. Oops, sorry. So if you're going into the monitor mode, the first thing you have to know is, am I coming from the secure world or am I coming from the normal world? And for that, we're using the coprocessor 15, which got an additional register with TrustZone, the so-called SCR, Security Configuration Register. In that case, these are like the first 4 instructions. See if I'm coming from the normal world, and if yes, switch into the to secure code, and otherwise go to the normal mode. The next thing you have to do is store the state of all register banks. If you remember earlier, I said that it's like having 2 register sets for the CPU. That's actually not true, because they are still the same registers, but the monitor mode stores the register state of either this normal world or the secure world, and so the monitor just switches them out for you and saves all the data. And because of that, you have on each monitor call, on each context switch, you have to go through all CPU modes, like supervisor mode, interrupt mode, and store the registers, and vice versa for restoring. So it's quite a thing until you are in the rootkit and back. You have to store the normal world register, switch on the NS bit, so enable the secure mode, restore the secure world registers, execute the rootkit code, store the secure world register, switch off the NS bit, and restore the normal world, and then go back to the execution of the normal world. So you can imagine this is quite some code you have to run there, and yeah, performance is very critical. Another thing is, if you're doing stuff on the monitor, be very aware of cache and pipeline stuff, because if you don't use pipeline flushing instructions and you switch back into the normal world, the instructions might get executed in the normal world, and for instance via JTAG or something similar, you could actually see the instructions getting executed, and immediately someone will know, okay, there's a rootkit. And be sure to have your cache configuration right, because the QEMU cache support is, I think, quite experimental. And so at first, when I was switching back from both modes, I still had my secure stuff in my caches and was able to access it, which was quite bad. For me, the most interesting part and most fun part was locking down the trust zone and configuring everything that it's as unsuspicious as possible. So even though you can't prevent the user from knowing that you actually have trust zone in the chip, but you want to behave like, yeah, we're doing nothing here and everything looks normal, and you don't really want to lock him down. I mentioned earlier there's the security configuration register on the coprocessor, and two of the things that it allows is the modification of the A and the F bit in the CPSR, yay passwords. CPSR is the current program status register, and the A and the F bit are 2 bits to disable fast interrupts and abort interrupts. And yeah, as said, if you configure a hardware timer to always call your rootkit, and it triggers a fast interrupt, if you set this bit, you are able to prevent the normal world from disabling the interrupt. But in my opinion, that's quite suspicious, and so I wouldn't do it. Yeah, but you can also set the world for all interrupts. So no matter what interrupt, you can say, okay, please jump into the secure mode, and the normal world is not able to tell to read out the register to see whether the interrupts are immediately going into the normal world or into the secure world, which comes in quite handy as you can perfectly hide your scheduling scheme. It also contains the actual NS bit, so you can, if you're in the secure world, you can actually immediately set the NS bit to fails and be back in the normal world if you have something timing sensitive. That can be handy. In my case, in my rootkit, my demonstration rootkit, I don't lock down things at all. I just say, okay, all interrupts go into the monitor mode, so no interrupt at all is immediately going to the normal world, because with that I have a constant delay on all interrupts, which is, I think, the most unsuspicious thing to do. And as said, I decided to allow the normal world to mask some of the interrupts. Depending on the hardware, you may need some additional configurations, like TI with the OMEP processors integrates a lot of additional stuff in the CPU for like crypto stuff and so on. I don't know what exactly, because you would have to sign an NDA with them, and I still want to do my open research. So yeah, if anyone has a contact to TI and can get me a demo and software development kit for TrustZone without me signing an NDA, I'd be glad to hear from you. But, there's also a TZPC, TrustZone Protection Controller. Yeah, it does some memory configurations and some peripheral configurations, but it's not really interesting and quite boring. Yeah, and after we locked down the trust zone and made sure that the operating system won't notice us, we actually start the operating system or the operating system loader. The cool thing is that the operating system is unmodified. You don't even replace something in memory. You don't touch it at all. The operating system is entirely virgin. And yeah, for the operating system, nothing to see here. So what do we do now? We have an execution environment that is entirely separated from the normal operating system. We have configured the CPU and its peripherals to hide any traces from our existence. And we get control of the CPU regularly and can do whatever we want. We can access all user data, manipulate data, memory, and code. For instance, if I experimented with some mandatory code signing stuff, and you can just disable it from within TrustZone, because you can just flip some bits in the RAM and everything will be fine. Which can be cool if you write malware for this kind of stuff. And we can communicate, which is a very difficult topic, because you can't just use the network interface. That will be obvious as shit. So, yay. Communication is a very difficult topic, and I was really thinking about just ignoring it and hoping that no one would notice, but after thinking it for a while, there are actually 3 chances. The first one is use NFC. So if you have a really targeted attack, you could, for instance, use the NFC terminals at a supermarket, which no one uses, to drop off informations. The next thing is talk to the baseband. I tried this. This is quite complicated to configure the baseband, to do additional connections to the outside world without breaking the bonding between the normal operating system and the baseband. And I did manage to send data from the secure world, but I did not manage to restore the state into something useful for the normal world. But interestingly, on the thing where I tested it, it just resets the baseband and there's not even an error message. So it's quite cool, especially because no one has the hardware to sniff UMTS, and you have UMTS everywhere. And yeah, open communication. You can load your modules, you can load whatever you like directly from the internet using the baseband without anyone noticing. At least from what I experimented with. You can create IP packets by directly talking to the network hardware. The Cloaker guys, I mentioned them earlier, do exactly this. But it's so suspicious, because if you're doing it over a wireless network or over cable network, yeah, people will notice. You just need Wireshark to detect the rootkit, and that is not cool. Yeah, now we're slowly coming to the end. Ports to new hardware. Diversity in the Android field is a good and a bad thing, and the cool thing is that trust zone looks the same everywhere. So if you write your rootkit, you can use it everywhere. You only need to replace the hardware dependent things like communication stuff and some memory settings. It's very easy. I tried several QEMU configurations and was able to just replace the parts that had to be changed in a day. Yeah. A quite interesting thing is integrating the rootkit in an actual trusted execution environment. For instance, by modify the Open Virtualization TEE. That is what I'm right now working on. Actually building a trusted execution environment that looks and behaves like a trusted execution environment, but in addition provides facilities to do off-band communication, to load code after itself, and I will open source it once it's in a state where there's not so much fix me in the code. Yeah. And the last slide, detection methods. I thought for me the most obvious thing is latency, because latency is always there, and if you want to execute something, you can't prevent latency. Unfortunately, you can't also just use the other 3 cores in the normal world and do secure stuff only on the first core, at least as far as I know. So yeah, you can't run secure world and normal world at the same time, even on a multi-core system, at least according to the documentation. I unfortunately don't have test hardware for that. Yeah, and you could also be paranoid and only use phones that don't have trust zone. I think that's impossible. Maybe Apple devices, but yeah. If anyone has some interesting attack vectors for detecting the thing, I'd be very interested for some discussions, and thank you for staying so long. Questions or anything? Yep.
Why would
Sorry.
you hide certain modules like communication module in the normal world and use it in the secure world?
Because then you in-memory analysis tools running in the kernel would be able to find me.
But can't you trip them? Can't you?
Yeah, but you wouldn't be able to trip everything, because you would have to know what the an analysis tool does, and that's impossible to predict, because there are like a million possibilities to tricking it into showing that it was modified.
The device from Trustzone know that this exploit is actually used
It's not an exploit, so it's actually by design. And for me, there's this one quote, I found it, I think 2 days ago. So at the very end, where I just was looking up some facts to make sure I'm not telling any wrong facts. And for me, this quote where they say, you can also run TrustZone invisibly to the normal world, for me it's obvious that they also think about such stuff. But I could be wrong, so I don't want to say that ARM is planning to rootkit us all or anything. Yes?
So from installing a rootkit like this, I mean, you would need physical access to the phone to be able to get down to the TrustZone layer, or is there ways to
well, you can... actually, you have to break the boot chain, because that's needed. The TrustZone is initialized so early in the process. You could also hack into a TEE, which is quite an interesting project, I think. So if you happen to have a phone and the TEE SDK, I think it might be interesting to fuss a bit around with the interfaces. But yeah, as I said, for me it's a highly targeted thing, or maybe like Carrier IQ, which was integrated by the vendors and the operators. So, but I don't have a way to just go to your phone and install it now immediately. Yeah. Yes?
What's your personal smartphone OS?
Oh no, this is embarrassing. I'm actually using an iPhone.
Is that because it's a secure environment? Paranoia, or because you just...
Personally, I'm not doing interesting stuff on my phone, yeah. But I like, on the one hand, the usability for sure, but I also like the kernel level security that iOS brings with it. I mean, for me, iOS invests so much time and force into securing the operating system, even though they still have embarrassing bugs with a freaking lock screen, and they should be punished. But
yeah. Jailbreaking the iPhone. Have you ever bothered jailbreaking your iPhone?
You must jailbreak your phone if you want to do some runtime analysis.
Do you jailbreak your phone?
This one not, but I have also iOS devices that are jailbroken. But this is still running iOS 5, so it's insecure anyway. Don't hack me. Yeah. Any other questions or further? Okay, then thank you. Thanks.